Hi, this video defines the directed graph abstract data type. This is going to be the data type that we're going to implement to represent graphs with data structures. So this video is going to cover a directed graph abstract data type. We're going to start with directed graphs. Later, we're going to see a container adapter that allows you to represent an undirected graph using a directed graph data structure. So there's a situation here kind of like map and set. You might remember that we started with the map abstract data type with keys and values, and we defined two competing data structures to represent a map, a binary search tree and a hash table, and compared them. And after we did all of that, we defined the set abstract data type, and it was really easy to implement a set once you had a good map. There's a similar situation here. We're going to define the directed graph abstract data type. That's a graph with these arrow one-way directed edges, and see two competing data structures for directed graphs. Once we do all that, we'll see that it's easy to adapt a directed graph data structure to become an undirected graph data structure. There's a common notation used here, which is n is the number of vertices in a graph. So this directed graph up here has 5 vertices, and m, it's unfortunate they sound similar, but it is what it is. M is the number of edges. If I count the number of edges here, it comes out to 6. Vertices are indexed 0 through n minus 1. So just like in the sketch here, every vertex has a different index starting from 0, just like array indexes. So here are the operations that we want to implement. First, we can create given n. That creates a new directed graph with n vertices and no edges at all. This is a little bit different from many of the other data structures that started out empty. Instead, with our graphs, when you create the graph, all the vertices are pre-populated. You have to say how many vertices there will be, and the graph starts out with vertices but no edges yet. Vertex count is an accessor that returns n, the number of vertices. Edge count returns the number of edges. Has edge ij returns true if there is an edge from I to j, false otherwise. So I and j need to be legal vertex indices. I has to be 0 through n minus 1, and j has to be 0 through n minus 1, and those define a pair of two vertices that might have an edge. Has edge returns true if there is an edge from I to j, false if there's not an edge from I to j. Remember that this is a directed graph, so has edge needs to pay attention to the order of I and j. It's from I to j. Add edge is the way that we add an edge to the graph. Add edge ij takes two vertex indices and adds a directed edge from I to j. Remove edge ij is how you can remove an edge. So removes the edge from I to j, and this is intended to be called when you know there is an edge there, so it throws an exception if there is no such edge. Out edges of I returns a vector of every j such that has edge ij is true. Another way of saying this is that it's a vector of all of the vertices that have an outgoing edge from I to that other vertex. And in edges is the other way around. In edges of j returns a vector of every I such that has edge ij is true. So in other words, it gives you a vector of every index that is having an edge from that index into j. So just to kind of illustrate this, here's a graph with kind of a nice drawing to it. Has edge tells you if there is a edge between two vertices. So has edge 1, 3 would return true because there is a directed edge from 1 to 3, but has edge 3, 1 would return false because there is no edge going in the opposite direction. Has edge 0, 10 would return false because there's no direct edge directly from 0 to 10. Out edges gives you the list of outgoing edges. So for example, out edges of 6, if I call out edges of 6, I would get a vector containing 7 and 9 because there are two outgoing edges of 6 and they end in 7 and 9. Or out edges of 8 in the center here would return a vector containing 7 and 5 because there are two outgoing edges from 8 and those two edges end at 7 and 5. In edges is the incoming edges. So for example, the in edges of 8 in the center would be a vector containing 2 and 4 because there are two incoming edges to 8 and the origins of those are 2 and 4. Or in edges of 3 would contain a vector of 1 and 2 because there are two edges coming into 3 starting at 1 and 2. So here's a little preview of the data structures that we'll cover that implement this abstract data type and what their runtimes are. We're going to go into this in more detail later, but basically there's an adjacency matrix that uses a matrix, an n by n 2D array to represent the edges, and the competitor is called an adjacency list. The adjacency list uses a vector of linked lists to store the edges, kind of like a hash table is a vector of linked lists. And you can see that they have different runtimes. So there's some definite trade-offs between the two.